So now we're ready to take on our first numerical method for initial value problems. So remember that this is how we define the initial value problem. Okay, it's defined by this function f of two variables, where t is the independent variable. We're always going to call it time. And it's in the interval from a to b, which is given. And u at the initial time a is also a value u0 that's given. And throughout, we're going to assume that u is just a scalar, although that's not actually very important, but it's convenient. And our numerical method is going to give us back values u0, u1, and so on, and a sequence of times t0 up to tn. And so the idea is that these values of u are approximate values of the solution at these times. Now, in order to help us keep notation straight, for the exact solution, I'm going to put a hat on the u. So u hat is the exact solution of the initial value problem. And then u sub I is meant to be an approximation to the exact solution at time ti for all the different values of I. And we're going to assume, for a while anyway, that the difference between adjacent t values is a constant h. So h has to equal b minus a over n, just like we did with the trapezoid rule, for example. Okay, so with that, we will look at our differential equation once more. And the strategy is going to be to replace the derivative with a finite difference. So let's just evaluate the exact solution at time ti. Okay, so we'll use a finite difference here. And then our solution will no longer be exact. So what we'll say is that the value of the solution at time I plus 1 ought to minus the value at time I over h. That's the finite forward difference for u prime at ti. And that should equal the right-hand side here. But we don't know the exact solution, so we have to put in the most recent approximate solution. All right, now, if you stare at this, what this tells you is that given ti, which we can already compute, and ui, we're given f as part of the problem, so we can rearrange this equation and solve for ui plus 1. And so what we have is a recipe for marching ahead one step in time. And since we're given the initial value of u, that's a whole algorithm. So the algorithm is to let u0 be given, and then just rearranging that finite difference equation, ui plus 1 is ui plus h times f of ti ui. Together, these form Euler's method. Now, Euler's method is a useful method for getting started and for understanding things, but it is not a useful method in practice. So we're only temporarily sticking with it to help us get our feet wet, but then we'll do more practical methods after that. Okay, let's look at how to understand what the error in this method might look like. So now what we can do is substitute in the exact solution back into the iteration formula. All right, so that means u hat at time I plus 1 minus u hat at time I minus h f of ti u hat at ti. Well, equals what? Well, if we were putting in the numerical solution, it would equal 0. But we shouldn't expect that of the exact solution. So hopefully, it'll be small. That's what we should hope for. All right, well, what does it equal? This is, by Taylor's theorem, and using the fact that ti plus 1 is ti plus h, then we get this stuff here. Okay, there's the first few terms, minus u hat ti minus h f ti u hat ti. Okay, and now you see that the u hat of ti's cancel out. All right, but also this term and this term are equal thanks to the ODE. Oops. So they cancel out too. And so what we're left with is 1/2 h squared u hat double prime of ti plus third order terms and higher. And now we're going to use this to define a quantity called tau I plus 1. And you notice that we factored an h out in front. We'll explain that in just a minute. But this quantity here is called local truncation error. So it's not 0, like we would hope it is if it were exactly true. It comes from the fact that the Taylor series had to be truncated in order to get here. And it's local because it represents what happens in just one step. So this is the effect. This is the error in a single step. So, of course, local error is pretty easy to measure, or pretty easy for us to compute, at least estimate to the most significant order. But what we're really interested in is what we call the global error. So what's the difference between, let's say, the exact solution at the final time minus the numerical solution? So we might call this the global error. Well, in order to understand what happens, let's look at a picture. This is just a conceptual picture, really. So we're given some initial point. So that's the point AU0. And then the solution to the initial value problem goes from there. So this is the exact solution that we want to track. Well, the first thing we do with Euler is we take a step. And one interpretation of Euler is that you follow the tangent line out a ways and stop. So this would be T1, U1. Normally the error might not be that big, but I'm exaggerating it. Now, once we've reached that point, we've jumped to a different solution curve, right? So we've kind of already lost our ability to track the original. But we go on, so we take another step. And this time maybe we got a little lucky and ended up getting closer. And so on. So you see there are really two effects to consider. So each local error is propagated propagated by the ODE. So it's not a matter of simply accumulating them. They actually shake things up a little bit. And we also have to take n such steps. So note that n is b minus a over h, which is O of h to the minus 1. And this is the reason why in the definition of the local truncation error we divided by h. So what we're saying is, in effect, if I cut h in half, well, I would expect things to get more accurate. But on the other hand, I'd have to take twice as many steps. So in other words, if the error only went down by a factor of h, then I would give that factor of h back when I took the n steps. So we're dividing by that h to sort of already account for the fact that we're taking n steps. So this is already accounted in the definition of tau I plus 1. But this flow is a more complicated thing. And it turns out that we can bound the effects of the propagation, at least for certain problems. And the theory is covered in the book. But basically the idea is that as long as things don't go too crazy when you change these solution curves, like with discontinuities or something weird, then in fact the effect will be bounded. However, there's a big gotcha. The bound can be exponential in the length of the time interval. So one way of thinking about this is a weather forecast, right? You could probably hope that tomorrow's forecast is reasonably accurate, but you probably shouldn't trust one that's 10 days out, right? And that's just because in this dynamical system of weather, a change in the path, a small error in the calculation, will eventually push us way far away from the curve. A bounded amount, but so large that it's effectively useless. So that's a bit of a gotcha, and there's not much we can do about it. In fact, that's built into the condition number of the initial value problem. Okay, so the upshot is, the bottom line, the leading power of h in the truncation error, the local truncation error, is the order of accuracy in the global error. Or let's say of the solution for all t in the interval. And so, fortunately, that's a really good thing to know, because we can calculate the order of accuracy or the local truncation error very easily through routine Taylor series. And so we know at least the behavior as a function of h of the numerical method on the actual problem that we're trying to solve.